Hello students, welcome to Trunkie Academy. I am Dr. Pallavi Kulkarni, your chemistry teacher. Today we are going to discuss the next topic from the hybridization concept, and that is we are going to discuss the another type of hybridization today. In the last two classes we have discussed or we have finished the uh, two types of hybridizations. First one was the sp3, next one was the sp2 hybridization with the help of example. Today we are going to discuss the another type of hybridization, and that is nothing but in a last two sessions we have finished sp3 hybridization. Example methane. Then we have also discussed sp2 hybridization. Example ethane, right? Yes, now today we are going to start with the sp hybridization. Okay, sp hybridization. Now for sp hybridization, first of all we will discuss one example for carbon containing compound, and then we will see another example with the another element, right? Not carbon and hydrogen but another elements in it, right? Okay, let us start the example, and that is nothing but acetylene molecule, or it is also called as acetylene is the common name. Ethyne is its IUPAC name. The molecular formula of acetylene is C2H2. There is a triple bond present in acetylene molecule. Okay, yes, always remember when there is a triply bonded carbon atom is always sp hybridized carbon atom. I will repeat, triply bonded carbon atom is always sp hybridized carbon atom. Okay, triply bonded carbon atom is sp hybridized carbon atom. Just I will show bigger structure. Yes, so these are the three lines or bonds present in between two carbon atoms. Okay, and they are further attached to one hydrogen each for satisfying the tetravalency. Now here if you can observe, there are two sigma bonds connected to each carbon atom and hydrogen atom. Now in this triple bond, always remember there is one sigma and remaining two bonds are pi bonds, right? So there are one sigma and two pi bond present in this molecule, right? So as I have told you, for the formation of the sigma bond or single bond, sigma bond we require the hybridized orbital, whereas for formation of the pi bond we require the unhybridized orbital, unhybridized p orbital with single electron, right? Unhybridized p orbital with single electron. Okay, therefore here how many for each carbon 1 and 2 sigma bonds are required, and for each carbon 1 and 2 pi bonds are required, right? Okay, so here two hybridized orbitals, with unpaired electron, two hybridized orbital with unpaired electrons are required for formation of two sigma bonds, while this is for each carbon atom. Okay, this is for each carbon atom. Okay, while two unhybridized p orbitals are required, obviously with unpaired electron in them, with unpaired electrons are required for formation of two pi bonds, right? Yes, so this is the requirement with each carbon atom. Now let us see what is the case with the carbon atom. So this is carbon atom whose atomic number is 6. Electron configuration is in the ground state. Okay, electron configuration, ground state electron configuration is 1s2, 2s2 and 2p2, right? This is the electronic configuration of carbon in its ground state. Now here this 1s2 is the inner shell or inner core, which does not take part in the chemical bond formation, whereas 2s2 2p2 is the valence shell which take parts in the chemical bond formation. Therefore I am drawing the orbital notation for the valence shell only. That does not mean the inner core is not present there. It is present, but I am not showing it to avoid the crowding and confusion. Okay, I hope you understand. Yes, so in 2p how many electrons are there? 2 single electrons are there. Right now with this you can see there are only 2 electrons in 2p orbital. That means it can form only 2 bonds. But as we know carbon is tetravalent in nature, it should form 4 bonds. Therefore there is need of excitation. Okay, there is need of excitation of electron. There is need of excitation of electron. Excitation of electron from lower level to the higher level, whereas the excited electron has a vacant box also. Okay, therefore there is possibility of excitation also, right? Therefore there is, because the excited electron should have a space after its excitation, that is empty orbital. So there is possibility of excitation also. Okay, possibility of excitation of electron also, right? Yes, so these two things are there. Therefore what happens, electron from 2s, one electron from 2s is shifted from 2s level, just a minute, it shifted from 2s level to 2p level to 2pz. Okay, like this, and we are getting the excited state configuration of carbon atom. Okay, so this is your carbon. Let us see its excited state electron configuration. Excited state electron configuration, 1s2 is there, but I am not showing its orbital notation just to avoid the crowding. Okay, yes, 2s1 and 2p 1 2p3. In 2s there will be only one electron now, and in 2p there will be 3 electrons, right, after excitation. Okay, so this is the excitation. After excitation there will be 4 unpaired electron in case of carbon atom, right? Okay, that is the required condition. Now you can see how many hybridized orbitals are required, only 2. How many unhybridized are required, 2. So therefore here, as only 2 are required, only 2 will combine with each other. Okay, yes, so what will happen, these 2 boxes, they will combine with each other. That means they will undergo hybridization like this. Okay, and after this we are getting the hybridized state configuration. Hybridized state electron configuration. Okay, so in hybridized state it will be 1s2 and I'll show only hybrid orbitals, that is these 2 boxes will combine with each other like this, and these remaining 2 boxes, that is remaining 2p orbitals, will remain as it is with unpaired electron, right? So this is the hybridized state. As you can see, which orbitals are combined in hybridization, 1s and 1p, that is we are getting sp hybridization, right? What is this hybridization called as? Sp hybridization. right? The name of hybridization is sp hybridization, and as two atomic orbitals are combined, we are getting two hybrid orbitals. Two sp hybrid orbitals are produced, right? Two sp hybrid orbitals are produced. Two sp hybrid orbitals are produced. Okay, yes. And what about this remaining two? These remaining two are, this is 2py and this is 2pz. Okay, yes, these two are unhybridized p orbitals, right? Unhybridized p orbitals, which will be utilized for pi bond formation, right? Okay, now let us see how the both the carbon atoms will show this kind of hybridization, and now they are involved in chemical bonding, right? Okay, one carbon atom I'll show like this here. Okay, now the geometry, I'll write down the geometry, that is shape of sp hybridized carbon atom is linear. Okay, linear, that is in one line. Geometry is linear. Okay, yes, linear means what? Both the hybrid orbitals are in one line like this. This is one hybridized orbital. Sorry, this is one hybridized orbital, this is another hybridized orbital of one carbon atom. Similarly, the another carbon atom also will have the same thing. Linear geometry means in one line like this. Okay, so out of which what will happen, one out of the two hybridized orbitals, okay, out of the two hybridized orbitals, one will be utilized for the bond formation, sigma bond formation with the carbon atom, neighboring carbon atom, whereas another will be utilized for the pi bond formation with sigma bond formation with hydrogen atom. Okay, yes, so this is the hydrogen atom. So one hybridized orbital will be utilized for the sigma bond formation with the hydrogen atom, two hydrogen atoms, right? Okay, so this is how we are getting two sigma bond formation here. So this is one sigma bond formation, this is the another sigma bond formation, right? Okay, now what about the remaining two orbitals? Okay, now as we know, py and pz are not in the same plane in which the hybridized orbitals are present. They are perpendicular to the plane, right? Okay, so py, first of all we will see it is also perpendicular. So py I'll show like this. So one lobe of py will be up, another lobe will be down. So this is py orbital of one carbon atom, and this is the py orbital of the another carbon atom, right? So this is py orbital containing single electron, right? Okay, so this is the 2py orbital of one carbon, and this is the 2py orbital of another carbon atom. There will be attraction in between them, lateral overlap like this. There will be a lateral overlap, parallel overlap like this, like this. Okay, so this is the first sigma covalent bond, right? This is the first this is the first pi covalent bond, right? Okay, the another orbital is also parallel to the this one, right? Okay, perpendicular to this plane, right? So this I'll show like this, one lobe here, another lobe here. Now as this is a 2D board, or this is a 2D surface, I'm not able to show the three-dimensional image of this orbital, but I hope you can understand this p orbitals are perpendicular, they are in another plane. That is, if for example this is present in x axis, this will be in y axis, and this one will be in z axis. As we know, x, y and z axis are perpendicular to each other, 90 degree to each other, right? Okay, so this is the same situation for these orbitals also. Yes, so this is the 2pz orbital of one and this is the 2pz orbital of other. So they are containing single electron, and there will be a lateral overlap in between them also, and this lateral overlap is called as the another pi bond, right? Yes, so there is a lateral overlap in between the another p orbitals, that is pz orbitals also, right? So this is how there are formation of two pi bond. This is one pi bond and this one is the another pi bond, right? Okay, so this is how the molecule of this acetylene is formed. Okay, in acetylene there are triple bond is present, bonds are present in between the two carbon atom. So this is how a triple bond is produced. Okay, I hope you understood it. So just take a screenshot of this page first of all. Yes, so let me just show you one by one. Yes, first of all take this one. Okay, now take a screenshot of this remaining portion. This remaining portion, take a screenshot together. Okay, now let us see one more example, another example containing the elements other than carbon. Okay, so other examples are beryllium compounds. Yes, another example we are going to see for sp hybridization. Compounds of beryllium, they also show the sp hybridization. Compounds of beryllium, they also show sp hybridization. Okay, examples are BeF2, BeH2 and BeCl2. Okay, yes, out of these let us discuss BeH2. Okay, the explanation for BeH2 beryllium hydride. Okay, yes, so here as you can see, beryllium is attached to two hydrogen atoms like this, linear geometry. There are two sigma bonds, 1 and 2, right? So as therefore, how many hybrid orbitals are required? 2 HO are required, right? 2 HO are required. Let us see the beryllium atom then. So beryllium atom, atomic number of beryllium is 4, electronic configuration is 1s2 and 2s2. Okay, the orbital notation, so this is the inner core which do not take part in the chemical bond formation. Okay, so I will not write down its orbital notation, whereas this is the valence shell. Valence shell take part in the, or electrons present in the valence shell take part in the chemical bond formation. Therefore I will write down the valence shell notation only in the ground state. So let us see the ground state electron configuration, 1s2 and 2s2. So 2s2 contains 2 electrons, one up one down, right? Okay, now here even if I have not shown, but 2p orbitals are also there, they are not containing any electron, therefore we do not show it here, right? Okay, but I will write it down now because we are going to need it. Okay, let me explain where we are going to require them. Okay, so these are the two p orbitals, empty 2p orbitals, right? Okay, now with this electron configuration you can see there is no any unpaired electron in the beryllium atom. That means it will not be able to show any chemical bond, right? Therefore there is need of excitation, right? Therefore there is need of excitation of electron because no any unpaired electron is there. Okay, similarly there are 3 vacant rooms available for the excited electron, therefore there is possibility of excitation also, right? Therefore there is possibility of excitation of electron also, right? Yes, therefore the excitation takes place, right? This electron enters from 2s to 2p. Now let us see therefore the beryllium excited state electron configuration. Okay, in this excited electron configuration there will be only one electron in 2s and one electron in 2p, right? Okay, therefore 2s will look like this and 2p will look like this. Okay, now in this case you can see there are 2 unpaired electrons in the beryllium atom and therefore this is how they can undergo the hybridization, right? Okay, now what will happen further? They are going to undergo the hybridization, right? Okay, as only 2 orbitals are required, 2 boxes will combine, right? Okay, so these 2 boxes will combine. Okay, and we are getting the hybridized state. So let us see the beryllium atom in its hybridized state. Okay, hybridized state. So these 2 boxes will combine with each other. They are containing single electron, right? As S and P are combined here, this is S and this is P, therefore name of this hybridization is sp hybridization. And as 2 atomic orbitals are combined, 2 hybrid orbitals are produced, right? Therefore 2 sp HO are produced, right? 2 SpHO are produced. Now what will happen with each this sp hybridized orbital? If I am writing the electron of hydrogen as cross, okay, so one hydrogen atom is going to combine with it, and this is how we are getting the BeH2 molecule. The geometry will be, yes, geometry will be what? Geometry will be linear geometry, right? Linear geometry means what? Beryllium at the center. These are the 2 sp hybridized orbitals of beryllium, and they are going to combine with hydrogen, So this is how two sigma bonds are produced here. Now this is a linear geometry. Now in this linear geometry, if you can see the bond angle, okay, this bond angle is 180 degree, right? Okay, 180 degree. The bond angle, hydrogen beryllium hydrogen bond angle is what? 180 degree. Okay, yes, it is equal to 180 degree. Okay, I hope you understood this example. Now similar to beryllium hydride, all other examples of beryllium are going to show exactly same kind of hybridization, and therefore their structure is exactly the same. Okay, with the linear geometry and bond angle is 180. Okay, yes, take a screenshot of this page. Okay, so I hope this concept of hybridization is clear to you. So we have discussed the three different types of hybridization, and first one was the sp3, second one is the sp2, and third one today which we discussed is sp hybridization. The next different types of hybridization, that is sp3d, sp3d2 and sp3d3, we are going to discuss. You are going to study that in the class 12th in the chapter coordination chemistry. Okay, so that's all for today. So before ending the class, I'll just show you the DPP, daily practice problem. So this is a teacher's portal which you can see right now. You have to go to resources, then on the left hand side all the way down you can see this one, writing material, wherein you can see DPP, daily practice problem. Just open it. You can download it also. You can write down the solutions on your notebook or any paper, then take a picture of that and just upload it on your portal so that it will be visible to teacher, and teacher will evaluate and let you know the suggestion and corrections wherever required. Okay, so that was about DPP, daily practice problems. So I hope it is clear to you, and whatever doubts regarding the hybridization concept are there in your mind, or whatever questions are there in your mind, please let me know in tomorrow's session or any other session. You can just note down all your doubts on your notebook, and collectively also you can ask me. I will explain each and every question asked by all of you. Okay, so that's all about the hybridization concept, and tomorrow we'll discuss another topic from some another chapter. And yeah, so that's all for today. Thank you so much, students, for your precious time. Thank you so much for joining. All the best to you, and take care.